In this skill, we're going to use all the ideas from the previous skill, except we're also going to do the calculations. A container of an ideal monatomic gas has a movable piston that allows the volume of the gas to change without allowing any gas particles to enter or leave the container. We're told the gas undergoes a thermodynamic process from state 1 to state 2, as shown on the pressure volume graph provided. Our goal is to determine the change in the internal energy, heat flow, and work done. Okay, so first let's go to our reference sheet and find our relevant equations. We've got 3 different equations that are going to come in handy for us here. Firstly, we have the equation for the total internal energy of an ideal gas, which is U equals 3/2 PV. So U equals 3/2 PV. And we're going to use that equation to figure out our internal energy from the graph. So looking at point 1, which is our initial point, that's here on the graph. We can read off our pressure from the y-axis of the graph. Our pressure at point 1 is 25 pascals. And we can read off our volume from the x-axis of the graph, which is 24 pascals. So in our equation for the initial internal energy, we're going to have 3/2 times the pressure, which was 25, times the volume, which was 24. If we put that into our calculator, we're going to get a total internal energy of 900 joules. Then we can do the same for the final total internal energy. It's also going to be 3/2 PV. So looking at our graph at point 2, which is our final point, for our pressure, we have 15 pascals, and for our volume, we have 4 meters cubed. So we've got 3/2 multiplied by 15 multiplied by 4. That gets us an initial total internal energy of 90 joules. So there's our initial and final energies. To find the change in the total internal energy, delta U, we're going to do our final U, UF, minus our initial U, UI. So our final U was 90, and we're going to subtract our initial U, which was 900. That gives us a delta U of negative 810 joules. So let's go ahead and fill those all in our answer boxes. We had 900 joules for our initial internal energy, 90 joules for our final internal energy, which gives us negative 810 joules for our change in total internal energy. So we figured all that out just from the pressure and volumes on the graph using U equals 3/2 PV. Our next step is going to be finding Q, the work done. Here on our reference sheet, we can see we have this equation for work, W equals negative P delta V. However, if we look in the definition for work, we can see the equation for work only applies when pressure is constant. Otherwise, we can find work by calculating the area under the PV graph. So typically we use the equation W equals negative P multiplied by delta V. But that only works if the pressure is constant. In other words, if our line on our graph were a straight horizontal line, then we could use negative P multiplied by delta V. However, we don't have a straight horizontal line here. So we're going to be finding this area in here and using that to figure out our work. So that area is the area of a parallelogram, which is calculated by half the sum of the parallel sides multiplied by the distance between them. So in this example, one of our parallel sides has a height of 15, the other parallel side has a height of 25, and the distance between them is from 4 to 24. So in other words, that's 20. So we've got half times 15 plus 25 multiplied by 20. Putting that all into our calculator gets an area of 400 joules. Now I need to think about the sign. Now remember, when the volume increases, that means we have negative work. When the volume decreases, we have positive work. In this situation, our volume has decreased from point 1, where it was at 24 meters cubed, to point 2, where it was at 4 meters cubed. So since our volume decreased, that means our work is positive. So our work is going to be positive 400 joules. If our volume had increased instead, then our work would be negative 400 joules. Awesome. So that's our work. We found it to be 400. Now we can go ahead and use the first law of thermodynamics to find Q. Here's the first law of thermodynamics. It says that delta U is equal to Q plus W. Delta U is equal to Q plus W. We're trying to find Q, so we're going to subtract W from both sides so that it cancels out on the right. That leaves us with Q is equal to delta U minus W. So putting in our numbers, delta U was negative 810, and we're subtracting from that W, which was 400. So that's going to give us a Q of negative 1,210 joules. So we can go ahead and fill that in our answer box here. Awesome. Okay, so we used our graph to figure out all of that. Next, we're going to just describe what happened. So our delta U was negative. That means that we had a decrease in the internal energy of our gas. Our heat flow, Q, was also negative. That means that heat flowed out of our gas. We removed heat. So heat was removed from the gas. The work done was positive. That means that energy was added to the gas. In other words, work was done on the gas by the piston. So you can see in these questions, we're using three equations. We're using U equals 3 over 2 PV to figure out our initial, final, and change in internal energies from the PV graph. Then we're using the work done equals negative P times delta V equation to figure out our work done. Remember though, if your pressure isn't constant, instead of using P delta V, you're going to find the area under the PV graph and then figure out the sign based on whether the volume increased, in which case we'd have a negative work, or if the volume decreased, in which case we'd have a positive work. Then finally, we'll use the first law of thermodynamics, delta U equals Q plus W, to find any other unknowns.